And I know I've been playing catch with like trying to post the previous lecture, the one before it. It's just been catching up on everything as I start to get more energy and be able to commit to work. I wanted to make a couple of announcements, comments. So there was a survey quiz that I put out called Muddy Points on Linear Solvers, where you guys put in what was most clear to you and what was the least clear to you. And we're going to do that for every chapter from Linear Solvers onwards. And we didn't do that for the first 4 errors because it was not kind of really that there wasn't much new stuff over there. But for linear solvers and moving on, we're going to do that so that I can get some of your feedback and try to address it before the exam. I think I sent the survey prematurely before homework 4, before you guys worked on homework 4, because many of the comments were saying, iterative solvers are not clear to me, but maybe because I didn't work on homework 4, which means, you know, you probably didn't review the slides to refresh your memory with what we discussed in class. So after homework 4 is due, which is this Thursday, I will reopen the survey again and give you a chance to update your answers so that I get the most accurate feedback, so that we can discuss it in due time and definitely before the exam. I want to, sorry, I'm catching my breath. That's kind of one of the weirdest thing with COVID is just you feel winded very, very easily. And again, I don't even have a cough, which is just so weird. So for homework 3, for all the homework assignments, I would starting homework 3 because those are the serious homeworks. I want to solve them in class as much as I can. Because we missed last week's lecture, so we're kind of gonna get slightly tight on time. I promise I want to do that, but today would have been the time to do it, but I'm gonna move that to Thursday. Okay, we'll discuss homework 3 because today I want to get started on interpolation. So I have enough material to assign you a homework on Thursday on interpolation. So I want to cover the material on interpolation first, and then on Thursday we finish off with interpolation, hopefully, and we you know, together we solve homework 3, and then we continue with homework 4 and so on. Okay, for your exam 1 is starting to approach. It's going to be in March, early March, end of February, something like that. I'll keep you posted and updated, and it will cover material from the beginning until interpolation. Okay, until we're done with interpolation, which is today, and probably Thursday we'll finish off with interpolation. Okay, with that, I'm going to share my screen and we can get started with the lecture. If you have anything to say, just open up your microphone and speak. Again, I cannot see your chat. Okay, I especially when I start the slides, it's kind of hidden. So please, if there's something you want to say, if it's important, just unmute your microphone and speak up. Okay. Okay, there's nothing on the chat here, at least right now. Okay, so let me share this other screen. Okay, perfect. And now, okay, so far we covered the topic of linear solvers. 1 second here. Let me just, if you don't mind muting yourselves, please. Okay. Okay, so far we covered errors and linear solvers, and there's a reason that I start with linear solvers, and I mentioned that one of these previous lectures ago, is that we're going to encounter linear systems in pretty much every chapter we're going to address from here onwards until the end of the semester. There's going to be a linear system of equations. Many textbooks in numerical methods, they put linear solvers or linear systems of equations sort of in the middle, which is also one way of doing it. But because we're teaching this in person, it's best in real time, it's best to do it in a manner where the pieces kind of start fitting together, okay? Speaking of fitting together, the next two chapters are gonna be on curve fitting. The first chapter on curve fitting is gonna deal with interpolation. And I don't have a fun story for interpolation because it's kind of obvious, but I have some learning objectives for you, and I'll go ahead and read them up. Before I read them up, actually, let me just say a word on curve fitting. The idea of curve fitting is you have a set of observed data. For example, the density of some gas you're looking at as a function of temperature, for example, or the temperature of, at your house or on your deck versus time of day, for example, or some measure of the viscosity of a liquid as a function of temperature or as a function of some other parameter you're looking at. So you measure those data discretely. Typically, you get like a table and you can get a scatter plot. And the idea of curve fitting is to try to describe those data using a mathematical formula in the absence of any first principles derivation. So for example, suppose you don't know how the density of this gas varies with the temperature. You don't have any, you're not using kinetic theory of gases to try to derive this. You don't have any other theory to describe this density or this property. The best thing you can do is observe the data, the trend, the pattern, and just try to fit a formula in it so that you can have a nice, clean, closed form formula that you can use to do predictions and look at to do predictions. If you want to extrapolate, that will be regression, or to do interpolation where you did measurements, for example, at a few temperature data points, but you want the data in between, you do interpolation. And that's the objective of this chapter. You will, at the end, hopefully, you will be able to define what it means to interpolate data. You'll be able to identify the order of the polynomial that interpolates a number of data points. We are only going to look at polynomial interpolations because polynomial interpolation, they're the most powerful, most widely used, and most easily comprehensible, and they do the job pretty much all the time. You'll be able to derive the system of equations that you need to solve to build a polynomial interpolant. And here's the kicker, is that's why we learned linear systems of equations initially. We're not going to use iterative solvers or those complex solvers. It's just going to be a simple A inverse here. But you will see that the formula to build an interpolant is the formula for an interpolant, for a polynomial interpolant, is derived from the solution of a system of linear equations, okay? You'll be able to list the benefits and limitations of both first order and higher order polynomial interpolants. So a first order interpolant is simply a straight line, right? And that's a first order polynomial. You'll be able to calculate by hand an interpolated value using linear interpolants because it's kind of just easy to do a linear interpolation. You'll be able to identify which points are best used when you're doing linear or quadratic interpolation. So you have a long table of data and you want to find some data point in between somewhere. Which points do you pick? The one before it, after it, 2 points before it, and 1 point after it, things like that. You'll be able to list the conditions for cubic spline interpolants, which are a set of very powerful interpolants. You'll understand why we want to switch to cubic splines, but you only need to list the conditions. Deriving the splines can be very cumbersome and annoying. And all of this, you will be using built-in Python code, which is great, simplifies a lot of work, but you should understand the theory behind those. And if you want to in the future, you can pretty much use this theory to implement your own code, but there's no need to do that. So we'll be using built-in functions to perform polynomial and cubic spline interpolation. Okay, so let's start with an example. This is a subset of data points that I've taken here at my house in Sandy a couple of Augusts ago, excuse me, and I was measuring the temperature on my deck. I did that as a function of time of day. So on the x-axis, you're seeing here time 0, which is midnight, and then 1 in the morning, 2 in the morning, 3 in the morning, and so on the x-axis. And the y-axis, you have the temperature in Fahrenheit. So around midnight, I get 75. Very nice. Very nice weather when I'm living here, because we're right at the tip of Little Cottonwood, so we get these very cool canyon winds in the evening. Sometimes I have to wear a hoodie, in July, just sitting outside at midnight. Anyway, it can get pretty chilly. But you see the trend here, starts at 75, 74, 73, almost exactly at the hour, and I kind of rounded things up a little bit so that they look very, very nice. Okay, so now I want to ask you this question. So we have the data at every hour of the of the day, at least here for the subset in the morning. And what would be the temperature? What is your best guess for the temperature at 5:30 a.m.? Okay, so you have the temperature at 5, you have the temperature at 6. What would be your best guess for the temperature at 5:30?
I would think somewhere in between 70 and 69, which is 69.5 degrees.
Okay, so 69.5. Who was that speaking? Sorry, couldn't see you.
Sorry, that was me.
Yeah. So it kind of makes sense. You're between exactly in the middle of the temperature between 5 a.m. and 6 a.m. right? So the best guess would be the average between 70 and 69. And the best guess would be 69.5, right? And that's exactly what I would have said. Okay. So now I'm going to ask you, what is the temperature at 5:17 a.m.? For some reason, you need that time. Okay, you need that exact time, and that's in terms of a numerical hour. That's at 5.28. Okay, at 5.28. And if you're looking at the x-axis, that's at 5.28. So you only need to describe how you would find that temperature. How would you do that? So you know the temperature at 5 o'clock, you know the temperature at 6. What is the temperature at 5.28? Just describe how you would do it. No takers?
Hi, this is Nathan. I would just
Hey,
use the
Nathan.
equation for interpolation.
Okay, so how would so what is that equation for interpolation?
So you take the slope.
Okay.
So like 69 minus 70 over 6 minus 5. And then you multiply by basically how far along you've gone. So 5.28 minus 5.
Okay. Does anyone disagree with Nathan? Okay. So what Nathan is saying is we just draw a straight line between 70 and 69. Okay. Find the formula for that straight line. And once you have the formula for that line between 70 and 69, then you can evaluate it at 5.28. Is that correct, Nathan? That's what you're trying to say. Okay, so now I want you to go ahead and do that. So a straight line is just a slope plus an intercept, right? So slope times the x value, which is the hour of day now, here in this example, and an intercept. I know some of you might have studied a formula for interpolation in school, and probably you derived it the way we're deriving it here. That's okay. Repeating something you know is not bad, but we're gonna take a different perspective here eventually.
The formula I remember for interpretation is you have y2 minus y1 over x2 minus x1 multiplied by x minus x1 plus y1.
Yes, that is the correct formula we're going to use here as well. But let's go ahead and derive it. So Rich, I would like you to at least try to kind of see how we obtained that formula if you don't remember that, or if you haven't done that in school. So, and again, this might be boring, but that's okay. Let's kind of build up together. So we need an equation for the line connecting the points, the pairs 570 and 669. So you draw a straight line and you say, okay, my straight line is t of x, that's, or y of x, whatever you want to call it, is mx plus b. M is your slope and b is the intercept. X is your hour of day. Okay. The slope is simply like Rich said, so that's 69, or what Nathan said as well. 69 minus 70 over, it's rise over run, right? So 69 minus 70 over 6 minus 5, or 70 minus 69 minus over 5 minus 6, give you a slope of -1 exactly. So it's going down at a 45-degree angle. And then, so now you have the slope, right? It's -1. So your formula is minus x plus b. To find b, you simply evaluate your formula at any one of the data points you're dealing with, right? Because that line by definition has to pass at points 570 and 669. So t of 5 needs to be exactly 70, and t of 6 needs to be exactly 69. So you plug that in, whichever one, and you get the value for b, and that gives you b equals 75. Okay. And finally, you say the temperature at x equal 5.28 or 5:17 a.m. is, you plug in, so minus x is 5.28. So you get minus 5.28 per 75 gives you 69.72. And that makes sense, right? Because as we see the trend of the temperatures the temperature is going down. And so at 5 o'clock, it's 70, and at 6 o'clock, it's 69. So at 5:17, it's 69.72. So that kind of makes sense. It's somewhere between, it's higher than 69, less than 70. That's exactly how you would do linear interpolation. So that's called linear interpolation. That's kind of how it's derived. Okay. So let's now just generalize this formula for any pair of data points. And again, it looks like many of you already know this. So we'll just rederive this formula, but I want to cast it as a system of linear equations. Okay. So given 2 points, x1, y1, and x2, y2, and what I want you to, the way I want you to think about this moving on, because it can get very confusing, x and y, and what is x and what is y, what is your dependent and independent t and m and temperatures and things like that. Always think of them in terms of independent and dependent variables, and what is known and what is not known. In this case, you know the data, you know your dependent variables, the y values, we call them y1, y2, etc. And you know your independent values, which we call them x1 and x2. You could call them anything, but those are known quantities, those are known data that are given to you. Okay, so given x1, y1, and x2, y2, find y of x equal mx plus b. So we'll do that together. So by definition, this straight line needs to pass by these 2 points. So at x1, y1, this equation needs to be satisfied. So therefore, y1 equal mx1 plus b, correct? And at point 2, y2 equal mx2 plus b. Now notice what I put in red over here, those are the unknowns, correct? So you don't know the slope and you don't know the intercept, and that's what you're trying to find out. However, you do know the x values and the y values, the independent and the dependent variables, those are given to you. So they're shown in black over here. So now, if you write this as a system of equations, and there's a reason we're doing this as we build up higher order interpolants, you get this very simple 2x2 system of equations, and you can solve for the slope and write it in this convenient form, y2 minus y1 over x2 minus x1, which is the slope, right? And then the intercept is the rest, y2 minus y1 over x2 minus x1 times minus x1 plus y1. You can combine those as separately as b, or you can write them in this convenient form over here. This is a pretty powerful formula, and I'm guessing that you've done that at school. it's very nice and handy. You're on the airplane and you get an idea, or you observe some data and you want to do a little calculation. I don't know who does that on airplanes. One time I wanted to do that. We were so it was a funny story. I was in China for a research internship, and our plane was really delayed on the way back. And they ended up upgrading us into a bigger airplane, the jumbo jets, and the pilot wanted to make it up for us. So he was flying at like very high Mach number for commercial airplane, and we ended up arriving on time. We were late like 2 hours for departure, but we ended up making it on time. So I was trying to estimate the Mach number, and I had to do some interpolation. So, you know, I'm one of those guys who can do who wants to do an interpolation on the airplane, but all I could do was a linear interpolation, right? So it's kind of, you don't have your computer, and there wasn't Python at the time. And so, you know, that's something you would do by hand. You're kind of trying to do a calculation in your head. You're doing something by hand. That's what's so powerful about linear interpolation. And honestly, I've used it very effectively, even when dealing with practical data, because all you need are just 2 points and you find the point in between. Now, when you have very sparsely spaced data and you don't have a lot of sampling points, then linear interpolation might not be very accurate, because it just draws a straight line between 2 data points, right? So, you know, if you take the data for the temperature versus time of day, you know, as the sun starts rising, that pattern becomes nonlinear. And if you're not sampling at a lot of hours, you know, let's say you sample at 6 in the morning and then at 11 and then at 4, you're going to miss a lot of the patterns of the temperature fluctuation as you go throughout the day. And in that case, linear interpolation becomes very not accurate at all. Okay. So that's kind of one of the disadvantages for linear interpolation, but it's very easy, very simple to use. Use it to your homework, you know, doing things by hand, etc. All right. So now, switching back and looking at more general motivation and concept for why we do interpolation. Oftentimes, like I said, a lot of data that we collect, a lot of data that is given to us is in the form of observed discrete values. I'm showing here a table from one of the classic textbooks in chemical engineering for heat and mass transfer, showing the properties of air at atmospheric pressure at various temperatures. So you see in the first column, you see the temperature in Kelvin going from 100 to 1000 in increments of 50 degrees. And then you have the density as a function of temperature, the thermal expansion coefficient, and then the viscosity, okay? So just different data, different properties. And so those data are given to us oftentimes, and we want to find some data in between. So let's say, you know, you want to find the density at 210 degrees, okay, or you want to find lambda at 531.3, or you just want a formula for all of those data, a nice kind of formula that you can use in your code, in your research, etc. This is where interpolation comes in, and the concept is simple. We're going to choose a polynomial function to fit those data, whether go through the entire data set, which is the only kind of way if you want to look at the entire data set, or if you want to look at subsets of the data, just fit a polynomial within those subsets and we will see the advantages and the disadvantages in that case, okay? And once you find that polynomial, now the polynomial is going to go through each and every point, and those are going to give us the conditions for what the coefficients of that polynomial are going to be. And once you know the formula of the polynomial, you can evaluate it anywhere within that data set, okay? And that is the concept of curve fitting via interpolation, okay? This is the plot of the density in this case, from this table, density versus temperature. Okay, so you see it kind of has a nonlinear pattern, looks almost like in exponential decay. Okay, going down at very low temperatures, the density is high as expected, and at high temperatures, the density is starts going down. Okay, linear interpolation. The idea of linear interpolation is very simple. Like we said, is you just connect the points with a bunch of straight lines. You take every pair of points and you just draw a straight line in between. And this is actually what you get, and that's a point I will make when we are using Python to plot. This is what you get when you plot your data and connect it with a line. You essentially get a representation of what linear interpolation would look like. You're just drawing straight lines between the points, okay? Now, the formula to get those straight lines is what we just derived a few slides ago, y2 minus y1 over x2 minus x1 times x minus x1 plus y1, okay? That's what you get now. For each pair of data points, you have a formula like that, okay? For each pair of data points, you have a formula like that. Now, we're not gonna write the code to do this because Python provides that capability through NumPy and through the function called interp, okay? There are other reasons why we're not writing code for this anymore. I don't think it is necessary. I mean, these functions are built in, they're verified, they're good and easy to use. We're just going to be using them as we move on. The function is called interp. I think in MATLAB it's interp1d, I believe. I forgot. But it has the following signature. It comes with the NumPy module. And the way I would use it is write it as ye equal numpy.interp, and I'm putting here xe, xi, and yi. What do I mean by those? This function needs to take 3 arguments, and it will produce a quantity for you. Okay, the xi and yi are your independent and dependent variable inputs. So those are the x input values and the y input values. So in our example, those would be, for example, the temperature and the density values. Okay, you can give it all of them. You just give the entire data set, and the interp function is going to figure out where you want to interpolate, and that comes through xe. That's where you want to interpolate. Okay, so that's your desired value. So let's say you want to interpolate the density at 532.3. xe would be 532.3. That's where you want your dependent variable to be evaluated at. Okay, so these 3 arguments are known quantities that you give into interp, and then the result of interp would be a dependent value at xe. That makes sense. So that's how I paired them: ye, xe, and xi and yi. Okay. To do this, let's just do it together with the interp activity 1 with gaps from the interpolation module on Canvas. So go ahead and download that, load it up on your Jupyter, and I will see you with the Pythonification. Okay. All right. All right, can you guys see my Jupyter notebook? All right. Do you want me to zoom in a little bit? Sorry, I didn't see that. Yeah, let me zoom in a little bit. Is this good? Okay. So go ahead and load it up. And I already have some code ready for you. Unfortunately, we can't afford the time to type this code up every time. It just becomes time consuming. I personally don't type it up, like these boilerplate stuff. I just copy them from a previous notebook and just move on. So just do that, and just forget about it. So I'm importing NumPy over here, but notice I'm also importing interp from NumPy. So you could either use np.interp later, or you just import interp if you don't want to use np.interp or numpy.interp. Okay. And this is the boilerplate for producing high quality graphics. Okay. Now what I've done here is already I created the arrays for the temperature and the density. Okay. So for the temperature, because the data for the temperature was given to us at fixed intervals of 50 degrees. So we started 100, 150, 200, 250, right? So I could create all of that entire array through a lint space. I don't have to input it by hand. However, for the density, I had to input this entire array by hand, starting from 3.5 kilograms per meter cube all the way to 0.3484, okay, 335. So if you print this, you can verify that my temperature is indeed 100, 150, 200, 250, etc., all the way to 1000, okay? And again, if you're in doubt, just print it out, okay? And then the density is simply this NumPy array that I put in by hand, okay? This could be read from a text file, for example. You know, these are NumPy features. Don't have to worry about that. We'll see. I'll give you a few examples of how to load up data from a text file when we're doing the regression, okay? All right. Now, the first thing you want to do when presented with data is get familiar with the data, okay? Essentially, you want to flirt with the data. You want to look at it, understand it, make hypotheses about it, try to just get familiar with it, okay? So I have like these two rules in the class. When in doubt, print it out. When you have data, plot it. I don't have this. If you come up with something that rhymes with data, please let me know, okay? But you know, when you have data, first thing you want to do is go ahead and plot it. So I put in some gaps over here for you to plot. I want you to plot the density versus temperature, okay? And so what I would do over here, I would put T over here and rho over here, okay? And this is what you would get, okay? Now, I advise you whenever you have discrete data, always plot it as a scatter. Okay, do not connect it with straight lines, because as we will see later in regression, in practice, when you're doing observations, you will get values that are kind of almost zigzag in nature. And if you put a straight line in between them, you're going to get a very confusing plot. Really, scatter data should be plotted as points on a 2D graph. And then you say, okay, you know what? It would look a little nicer if I connect it with a line, and then you go ahead and do that. But that's not always the case. So I always prefer to plot my data as a scatter, as just points, and then decide if I want to connect them with a straight line. Okay. So, and you do this, if you notice here in matplotlib.plot, I put the independent variable t on the x-axis, the dependent variable on the y-axis, and over here I passed KO. K is the color of the symbol that I'm using. K for black, it could be, you know, if you do blue, for example, would be B. If you want to do green, you would put G, for example. O is the symbol, okay? So that's a circle. I could do an S, for example, gives me a square, okay? I could do a star, you know, it's going to give me a star. Okay, so these are kind of little tips and tricks. I don't know necessarily what you're using in your plots, but you know, this is kind of a little neat shortcut to do this. Okay, now always plot with a scatter. However, to show what linear interpolation looks like, or what you can do is add a connector between these dots. Okay, and to do this, you simply have to add a symbol for the connector, which is a simple, just type in the minus sign on your keyboard, okay? And when you do this, this is what you get. You all following me? Not magic, but you know, just little tips and tricks. So I'm going to do this again here. T row, you type in \RHO. We discussed this in class last time. Press tab, and then do KO and dash. You know, you can do other symbols. You can do, for example, dash dot. Okay, you can connect it as a dash dot, or you can do a dot. It will be just, oops, oh, there's no dot anymore, or dash dash. You can do a dashed line, okay? So that's a quick little shortcut for doing these plots. But this is what linear interpolation would look like. So when you plot something like this, and so look at the beautiful curve, you're like, no, you're just showing what linear interpolation would look like. We're gonna show later kind of what a polynomial fit is gonna look like and how much smoother it's gonna be, okay? Now, every time you're plotting something, it's actually internally matplotlib is just only going to be able to connect 2 points with a straight line. Okay, all we do to present a cleaner version of a plot, we just pack more points to make it look like it's a smooth curve. Okay. All right, so let's do linear interpolation now. I want you to use the numpy interp function to find the density at 132 Fahrenheit. Okay, now remember interp, it takes 3 arguments, xe, xi, and yi. Your xi, yi are your input data, independent variable, dependent variable, and then xe is where you want to interpolate to, okay? If you're in doubt, just press Shift-Tab, and it gives you the signature. X is where you want to interpolate to. If you press Shift-Tab twice, it gives you more details. The X coordinate at which to evaluate the interpolated value. XP is the list of coordinate points that you know, and FP is the dependent variable values that you also know from observation. So go ahead, what would you put over here? If I want to interpolate at 132. Pardon me? Did someone say something?
You would put 132 right there.
Yeah,
And
so
then-
Jake, so 132, great.
And temperature for xi and
Mhm.
rho for yi.
Perfect. So it gives me 2.775, okay? Now, does that make sense? Well, let's look at the plot. Let's look at the plot. We can eyeball it first, but there's a nicer way to show it subsequently. So at 132, for T at 132, that's kind of really over here, somewhere over here, okay? And the density starts at 3.5 and then goes down to, so it should be between somewhere between here, between 3.5 and like 2.5, right? And 2.77 is probably just right around here, which is exactly what I would expect, okay? Now,
is there, do you have to convert to Kelvin? You have Kelvin on the
oh, I
temperature.
apologize. Yes, no, this is wrong. I apologize. I had that same mistake last year and I didn't fix it. Thank you. Good observation though, very astute observation. Yes, just apologize. This is just a typo, okay? These are given in Fahrenheit, okay? All right. Okay, now what interp did internally, it went through this array and found the 2 points that straddle the temperature 132. And it just did linear interpolation between those 2 points. It didn't care about any of the other points, okay? That's what it did for you. If you were to do this programmatically, you do have to sort the array, find where those 2 points are, et cetera, et cetera. You don't need to do any of that over here, okay? Interp takes care of that for you, okay? So what you can do now is to actually plot this value, okay, on top of your plot over there. So let's copy and paste this guy over here, okay? Let's copy and paste this guy. So that gives us the original temperature plot. Now, I want to plot it. I want to add plt.plot at 132, okay? And I want to plot the value of interp 132 0, okay? And I'm gonna do it as an R. There you go. This is our interpolated value. Make sense? Nothing beats visualizing something. It's so powerful. It is very powerful. When you can try to visualize something, just do it. Just do it. And nothing beats 2D visualization. We see this problem in my research where we're visualizing 3D fluid mechanics fields. It's pretty impossible to visualize. So what we do slices or we do streamlines and just kind of follow them and actually we debug our code from visualization sometimes. We say, this doesn't make sense here. It shouldn't be there. There's something wrong in the code. And then we try to trace that, okay? Okay, so now I'm gonna show you why interp is also pretty powerful. So right now we just interpolated at one value, 132. What if now you wanna interpolate at 123, 251, 443, 599, 609, and 899, okay? All of those values, all right? So what would you do? Now, if you remember, the arguments for interp, where the argument for where you want to interpolate to can be an array. It doesn't have to be a single point, okay? So go ahead and try to provide it an array. Could be just put it as a list, okay, and see what happens. So just put this as a list, your XE, where you want to interpolate at. Do I have any takers?
Would you want to put the array that you have on
Yes.
in the text above?
Yep, exactly. I'll just copy and paste it. Exactly. And then over here, you just put XE and then T for your independent variable input, and then row for your dependent variable input. Now, what do you expect this to return? So you evaluate this, you did the interpolation at all of those points. What do you expect it to return to you?
A vector
Yes, of what?
of all of the pressures
The densities.
or the densities.
Yes, yes.
For
Of the,
each of the specific temperatures.
exactly. If values of the interpolated density at all of those values. So when you print it here, when you print the return value of interp, when you print YE, is going to be 2.99, etc., all of those values. 2.99 is the density at 123 Fahrenheit. 1.39 is the density at 251. 0.78 is the density at 443, and so on and so forth. Okay, so to see this, go ahead and plot the points on top of the original data. Okay, so what I'm going to do here, plot the original plot, rho versus T, and over here I'm going to plot XE and YE, and look at that. So what I'm showing here in red squares are the interpolated values of the density at the temperatures that we sought to find the interpolation at. Okay. It's very hard for me to know where you're at with the code. If you do not speak up, there's no way for me to try to help you right now. Just whatever the question is, just, you know, speak up. Now is the time to do it, okay? Because we're in the heat of the moment, we're talking about it, we're kind of, you know, immersed in it. If you're struggling with something right now in the code, just please let me know. I cannot see your codes to be able to help you. Okay, so I'm assuming you all got this, okay? And it all makes sense. It all is visually correct. All of these interpolated points, they fall in line. They need to be between the two values. There's a reason it's called interpolation, because it's going to produce a value between those 2 points. If it goes above or below, then you have a problem, okay? By definition, it has to be between those 2 points. It's a straight line, okay? Okay, so now I'm asking you to create a linear space of 100 points for the temperature, and interpolate the data to those points and plot the data on the original graph. Excuse me. So this is more of a just, hey, you know, we can do this. If we can do it for 5 temperatures, we can do it for 1,000 temperatures. So I'm going to create a lin space from 100 to 1,000 because those are the temperatures that were given to us in the original data. If you remember, we had data for the temperature going from 100 to 1,000. It is illegal to go beyond those points. I mean, you can do it, it's possible, but I would not trust any extrapolated data based on interpolation. Interpolation cannot produce new knowledge. Okay, it only uses existing knowledge, and it's not gonna increase the accuracy of the knowledge that you have. Okay, so do not extrapolate. Do not go beyond 100 or 1,000 for this problem, or beyond the data that you have. Okay. All right, so when you do this, you just simply create a lin space now for XE, YE, you interpolate the data at all of those XE, and then you just plot them. You know, we really didn't do much. However, let me ask you a question now. What do you expect the interpolated value to be if we were to look at the points 100, 150, 200, 250? In other words, the points for which the data was given to us. What would be the interpolated value? What do you think the interpolated values are going to be? This more of a
value?
Yes, the value is given to us because by definition, the interpolant has to pass through each and every point given to us. So if you try to interpolate at the points given to us, it's going to return the value that was given to you by definition, right? It has to pass through those points. So you see here, this first red spot over here. You see that first red square over here? It falls right on that point, okay? Suppose you go and interpolate at T. So here you go. I'm going to interpolate at T. Oh, through an error over here. Enter at T. There you go. So I've interpolated at the same points that were given to us. It returned the same points. Look at the red squares. It returned the same points by definition, because an interpolant, whether linear, whether first order, second order, cubic, whatever, must by definition go through each and every point of the original data. Okay, so keep that in mind. Okay.
So does that work with the scatter plot when you have a scatter with a line of best fit that doesn't necessarily hit all the data points?
Pardon me, Matthew, can you repeat that?
A scatter plot with a line of best fit that doesn't touch every data point?
So, okay, so we are not talking about best fits. That's regression. That's going to be the next chapter.
Okay.
What we're talking about here is polynomial interpolation, specifically to interpolate this kind of data. I mean, that's a good point, because you're probably used to doing that kind of best fit. We're not doing best fits yet, because first we want to understand, okay, what if I have data and I don't, honestly, over here, I don't want a best fit, because I have a very nicely, very nice data that's presented very nicely. A polynomial interpolant in this case is way better than a regression line. Okay, even if you can figure out what a regression line would look like over here. Okay, so but for interpolation, it's not a best fit. Interpolation goes through the data by definition and then gives you a formula to figure out what lies in between. Okay,
I got it. Thanks.
Yes, perfect. Okay, we will hit curve fitting when we do the next chapter. Okay. All right, so now I have another question for you called the reverse interpolation. And the reason is, I want to challenge now what we've done so far. Suppose now that we want to find the temperature given a density value. So in other words, so what we had density versus temperature, right? That's kind of what we plotted. That's what we did. Now, suppose we want to find the temperature given a density value. So I want to reverse the problem. I want to tell you, okay, what is the temperature for a density of 2.334, for example? Okay, what is that? What is the temperature for at what temperature do you get this density? So for example, find the temperature at which the density of air at atmospheric pressure is 2.3364. The tabulated data should return T equal 150 exactly, okay? So you don't see the table, but from the table, if you look at the table over here, the 2.3364 data point, okay, that occurs exactly at 150, okay? So now I want you to use interp and invert the interpretation of T and rho as independent and dependent variable. Now do it the other way around, okay, and see what interp gives you. Was it clear what I said? So now I want you to invert the meaning of the dependent and independent variable. In other words, I want you to swap the meaning of T and rho. So now rho is the independent variable and T is the dependent variable. Now go ahead and use interp to find the temperature that will produce a density of 2.3364. We expect it to be 150 exactly according to the table, but let's see what interp gives us. So what would you put over here? In other words, if you want to see it with a plot, what I'm doing, I'm plotting rho on the x-axis and T on the y-axis. Sorry, the other way around. I'm gonna do it, yep, this way, okay?
If you put in 2.3364 and then rho and then temperature, it gives you 1,000, which
yes. Okay, so and then okay, Jake, hang in there with me. Okay, so yeah, so Jake is saying, yeah, put in 2.3364. That's where we want to interpolate to, okay, given rho and temperature. And what you get 1,000, right? And that's a problem. Doesn't make sense at all. Okay, if you look at this plot over here of temperature versus density at 2.3364, we should get, this is the point, we should get 150 exactly. Okay, this is this point over here. Instead, we're getting 1,000. Okay, and there's a problem. And the reason is that I'm gonna have to switch to the slides, unfortunately. Okay, so let me switch back to the slides and I'll explain better on the slides. And then we'll come back to Python. Okay, can you see the slides now? Okay, there's a big warning for linear interpolation to work when you're using the interp function, is that the data, your independent variable data, needs to be sorted in increasing order from small to large. And then your dependent values need to be sorted accordingly. Okay, so if we go back to this table over here, when we interpolated the density, our temperature was the independent variable and it was already sorted 100, 150, 200, 250, and so on. Your dependent variable previously didn't matter, was density, it was sorted, flipped up, okay, large to small, it doesn't matter, it's just data. But when we switched the meaning of rho and T, when we switch the meaning of rho to be the independent variable, it is not sorted in increasing order, it's sorted in decreasing order. Okay, so what you would need to do, we would need to give interp the data such that it goes from the bottom to the top. It goes from 0.34, 0.36, etc., to 3.5, but don't also forget to accordingly change the values of the temperature as well, okay? There's a great way to do this without having to worry about all of this, without even having to know what is inside the data and how the data looks like, because your data might not be sorted at all. It could be, might not be sorted in any direction, okay? It could be just all over the place. A very easy way to do this in Python, and it's called argsort from NumPy. It stands for argument sort, okay? So first you take your array that you want to sort, you apply argsort to it, and it returns the arguments or the indexing, the correct indexing that would sort that array. Once you have those indices, you will simply take those indices and apply them to any other array that you want to sort as well. So if you've ever done column sorting in Excel, if you sort one column, it tells you, do you want to sort all the other columns accordingly, right? This is what argsort will do for you, okay? So let's do it in Python and see how that works, okay? All right, so now we're back to this one, okay? So let's play around with this before I show you the form. So I said that, so if we print the density row, okay, it's going, it just so happens here to be sorted in decreasing order, but that might not be the case in practice. So don't take that for granted. Just assuming that this is an array, a randomly sorted array or unsorted array. To sort this array, you can call a sort algorithm. There's some built in, you can just sort one array, but because this array has other arrays associated with it, such as the temperature, you need to sort both of them in the same order as your sorting row. That's where argsort becomes powerful. So if you call numpy.argsort row and you press enter, it returns the indices that would sort this array in increasing order. What you're seeing here, you start 18, 17, 16, 15, 14, and so on. Why? Because it's telling you the last index should be the first one. That's how you would sort it. This index 17, which is 0.366, which would be the second value. Index 16 would be the third value, and so on, okay? So let me give you another example. Let's say you have an array. A is numpy.array, and let's say you have 4, 5, and then 3, and then 7. Okay, so this is an unsorted array. And then if you call numpy.argsort on A, okay, it's going to give you 2, 0, 1, 3. To sort this array, the first entry in the sorted array needs to be index 2, which is 3. And then the second entry needs to be at index 0, which is 4. The third entry needs to be at index 1, which is 5. And the last entry is at index 3, which is 7. So in other words, now, if I store these sorting indices in a variable called idx, okay, then all you have to do to sort A is to say A idx. This is so cool, and look at that. It sorted it correctly. So idx, the only reason you need it is if you want to sort another array that's associated with A now. So let's take another array B, mp.array, and let's say those are other values that correspond to 4, 5, 3, and 7. And let's call them 33, 71, 82, 800, or 82, and then 1.3, okay? A at idx gives you 3, 4, 5, 7. Now B at idx gives you the corresponding values, okay? So initially, the value that corresponded to 3 was 82. Now in the sorted array, the value that corresponding to 3 is still 82. This is very powerful. So what you do to sort an array, you first get the indices that will sort that array. Then you apply the array on those indices and any other array that's associated with that one, because you want to sort all of them in the correct order. Your arrays might be like A and B all over the place, not sorted in any direction. Okay, I cannot overestimate the power of arcsort. It's a very powerful tool. Okay, so going back to our problem, okay, for the density. So again, the density was, if you print the density, it just so happens to be sorted in decreasing order. To sort it in increasing order, I'm gonna use mp.arcsort row, call this idx, and then I'm gonna do row at idx. Now look at that, it sorted it in the correct order. Now I also need to sort the temperature, correct? Because I changed the order of row, I need to change the order of the temperature as well. All I have to do is do t idx, and it will sort the temperature. Okay, so now I can use this appropriately, as I'm doing here. IDX is mp.arcsort row sorted, I stored it in a new array, and I printed it, and t new, the new t that corresponds to sorted row, is t at idx. Okay, and now you see what you've got, and now you execute your interpolation at row sorted and t new, and you get 150. Okay.
I have a question.
Yes, Jake.
So T IDX is only reading the amount, the total amount of points that's in row and giving temperature points for those.
No. IDX is the set of indices that would sort row. Okay, in this case, those are the indices that sorted row. But because T and row were given to you as pairs, really, when you read the data, however you sort row, you need to sort T by the same order so that they remain pairs. So IDX gives you the array or the indexing that will sort row. Now we get that indexing, and we also sort T by the same order. Whether, however it's being sorted, however T ends up looking, doesn't matter. What we're worried about is sorting row, and then we sort everything else according to how we sorted row. Okay, so look again at the example AB. Think of them as pairs. Your pairs in A and B were 433, 571, 382, 7, 1.3. Okay, if you want to sort A, then you have to sort B according to the order you sorted A. Okay, so you sort A by increasing order. That's what arcsort does. You store that indexing, that sorted indexing in IDX, and then you apply it to both A and B, and it gives you the correct sorting. Does this answer your question, Jake?
Yeah.
Very powerful tool. Again, think of these as pairs. You had this table T, row, lambda, and viscosity. Okay. Same thing when you go to your Excel and put a bunch of columns and say, I want to sort this column. And it tells you, do you want to sort the other columns accordingly as well? So it's like you have first name, last name, right? And then you have a unit. And let's say you want to sort by unit, right? You have to sort all of the other names as well accordingly, right? So arcsort gives you the indexing, the indices that will sort an array, and then you apply it to all the other related arrays so that you still have a nice table. Okay. Okay. Any concerns about this code? Anyone still stuck? Okay. Perfect. So that's the caveat for interp. You need to have your data sorted in the correct order. Okay. You need to have your data sorted in the correct order. If I were Python, I would probably give the option to interp to automatically sort it for me. So I don't have to worry about anything. Okay. Just give me data and I will find the interpolant for you. Okay. Anyway. All right, so I'm gonna switch share now, the screen, and we're gonna go to the slides. With a few minutes left, we'll get started on polynomial interpolation. Sorry, we didn't get a chance to take a break. But I know if I take a break, we're gonna lose my energy right now. So that's what's been happening with this COVID. Okay. Higher order polynomial interpolation. So linear interpolation is still a type of polynomial interpolation because a straight line is a polynomial of order 1, right? It is a polynomial of order 1. Okay. Higher order interpolants essentially allow us to now extend our first order interpolation to second and higher order. With 2 points, we were able to fit a straight line. What if you had 3 points? I claim that you can fit a quadratic in it, or a polynomial of order 2. So given 3 points, x1, y1, x2, y2, and x3, y3, and a quadratic formula, a0 plus a1x plus a2x squared, I want you now to spend a minute to find the system of equations that we need to solve to find the unknown coefficients a0, a1, and a2. Again, remember the key feature of a polynomial interpolant. And that key feature is that it must pass through each and every point, through each and every data point that you're given.
Let's ask a question about that.
Yes, Maxime.
Are we going to assume that the parabola is going to start at every single point, or are we going to assume that it's just going to be one gigantic parabola for every single point?
You don't know anything outside the 3 points. It has to pass through point 1, point 2, point 3. Anything outside, we can't make any. If you plot it outside, it's going to be a gigantic parabola. You're right, but we don't care about those points. All you care about is the 3 points you're interested in. So make sure it passes through those 3 points. Okay.
Okay, thank you.
So remember, we're looking for a0, a1, and a2. So those are 3 unknowns. We obviously need 3 equations, correct? But you have 3 points and 1 property of the interpolant. The key property is that it passes through each and every point that you're given. So that should give you the strategy to develop that system of equations that I'm asking for. Follow the same strategy shown on the slide that we did for the straight line. Evan, are you happy because you won the lottery or because you cracked the problem? I feel there was tremendous
problem.
You cracked it.
Yes. Yeah, just excited.
Hey, do you wanna share with us?
Yeah, I just set it up in a similar matrix as the first one,
Okay.
with 1 x1 squared, and then on the next line 1 x2 squared, on the next line 1 x3 squared, and then the coefficient matrix is, or the variable, I'm not sure.
The
That was
unknown
coefficient.
vector. Yeah, the
Yeah,
unknown vector.
is A0, A1, A2 vertically, and then equals Y1, Y2, Y3.
Yes, very good. Okay, so how did you go about and obtain that result?
I just set up that Y2 would have to be, or that, you know, any given Y would have to be equal to this quadratic that you gave us here. Would have to be
Applied at
equal
the
to
corresponding
that.
axis. Correct. Excellent. Thank you, Evan. All right. So I agree with Evan, and many of you are also doing that, I'm pretty sure. So here's the description of what these 3 points look like, and I'm going to fit a quadratic between them. The formula for the quadratic between those 2 points at any value x is a0 plus a1x plus a2x squared. Because it should pass through each and every point, then that formula needs to be satisfied in each and every point. So just like what Evan did, you take that formula and you apply it at x1, should return y1. You apply it at x2, it should return y2. And you apply it at x3, it should return y3. And now you have 3 equations and 3 unknowns. So you put them next to each other, you build a system of equations, and you see a pattern now. Okay, previously we had 1x1 and 1x2, a0, a1, y1, y2. Now you have 1x1 squared, 1x2, x2 squared, but you have one more point, 1x3 squared, a0, a1, a2, y1, y2, y3. Okay, that gives you the system of equations, and you solve it, and you get, again, your objective is to find the unknowns, a0, a1, and a2. Notice we change a lot of nomenclature in this class. In the chapter of linear solvers, our unknown vector used to be x1, x2, x3, etc., and the coefficient matrix was aij, right? Now it's a different nomenclature, and that should not confuse you. Okay, let it not confuse you. Always think of these matrices as systems of linear equations. What are you solving for? You're solving for a0, a1, a2. So those should always go in the unknown column vector. Okay. All right. So now we can generalize this, and clearly there's a pattern, and it's obvious. You know, for 2 points you can fit a straight line. Excuse me, you got 2 unknowns. For 3 points you can fit a quadratic, so that's a second order polynomial. For 4 points you can fit a cubic, because you have 4 points, so you can add one more unknown, so you can add one more coefficient in the polynomial, so you get to order 3. For n plus 1 points, you can fit an nth order polynomial. So for 50 points, you can fit a polynomial of order 49. I would never do that, but we're going to talk about the pitfalls of that later. But that's the theory of polynomial interpolants. If you want to fit the entire data set, okay, if you want to fit the entire data set into a single curve, okay, so then you pass your polynomials through the entire data set, and your objective is to find a0 through an. So those are n plus 1 unknowns. Okay, you need n plus 1 equations, and you have n plus 1 points, and that's how you do it. So in general, for n plus 1 data points, you can fit a polynomial of order n at most. Okay, or for n points, you can fit a polynomial of order n minus 1 at most. Okay, an interpolating polynomial must, by definition, like I said, go through each and every point of the data. Now, we're going to have a lot of discussion whether it's a good idea to fit one big polynomial through 50 data points or 1,000 data points. It's a terrible idea, it turns out. And we'll prove why, we'll show why, but that's the theory at least. And the formula, the formula for the coefficients is simple. You solve the system of linear equations given by this coefficient matrix, Okay, the rows are kind of become obvious. 1 x1 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 squared, x1 cubed, x1 to the fourth, etc., all the way to order n, and each row corresponds to the equation of your polynomial applied at one of the points. So point 1 is for row 1, point 2 is for row 2, point 3 is for row 3. On the right hand side, you have the y values, y1, y2, and so on. Okay, we'll continue this discussion next week, next Thursday, and we'll finish off interpolation. Hopefully, we'll have time to go over homework 3. Okay, then hang out here for a few minutes. Thank you for your attention, and I really again appreciate your bearing with me through this COVID, and I apologize for the inconvenience of moving the lectures online. Okay, thank you so much.
Is there anything in homework 4 that that you didn't cover yet so far?
No, everything in